First of all, I thank you, Dr. Nagarjuna and the team for organizing a special uh, EBUS Conclave and providing me a lecture. So, my topic is more of a physics types rather than a clinical, but still I want to try to more useful the people who are just the budding pulmonologists and going to use EBUS in the future. Uh, I call a couple of my radiologist friend and then they advise me to change the topic, but I still take the opportunity to read it out because that is the way the concerned keep themselves updated. Uh, so you know the ultrasound is a sound wave, right? And it requires the medium to pass, okay? So, and the wave which transmit from a one medium to another medium and the parallel of his longitude, right? The velocity of the sound wave is depend on the density of the medium which is passed through, and the reflection of the sound wave occur when the one medium to the another medium. So you have a transphase, the half of the sound wave will get reflected, and that principle, the reflected sound waves, can be again captured by the transducer, which is used to produce a sound wave, and that sound wave convert into electromagnetic, and then as a picture you can see on a screen. And this is very highly operated dependability. So the some setting suits me, it's not suits the other my colleague. And the organ, the specific, the cardiac echo, they have a different the preset, all the modalities compared to the for the liver, and then for a spleen, and then for a soft tissue, and for the gynec sonography, and then vascular sonography, and obviously we have a EBUS one. So the transducer is the most important part. It's usually filled to produce about 2 to 20 or 2 to 5 or 2 to 10 megahertz of the sound wave, and that acoustic material here which produce the sound wave, right? That is a piezoelectric elements, and behind that it is a dumping zone. So it is going on a one direction, and then whatever the sound which pass from a transducer to the body, which is reflected, catched by the acoustic lens, and then converted into the image. So the image quality which you seen on a screen, it's improved by adjustment of the brightness of the field, right? And the gain. You see the microphone, right? The microphone is amplify your sounds, okay? If I want to speak with you, my voice is not going to go beyond. So this microphone is amplified my tone, my voice, and it's reach beyond that. So same thing, that the surface which amplified the echo signal which is returning from the body, modified it and produce a picture. And that is the play of the gain, contrast, and etc. This I am coming on my next talk. Sometimes the microphone can produce a more noise. So that's how, if you correct beyond the limit of the gain and a contrast, you have more of echogenicity and your picture is going to blur. Sorry for the quiz. So the velocity of the sound wave is a different medium arranging in the descending order. So it's air, water, blood and organ. So you have to arrange in a descending order based on the velocity of the sound wave in this medium. Wow, great. Your answer is somehow incorrect here. Why? Just let you know. The correct answer is the C1. So you can see here, is travel on the base of the density. So the air has a lesser density, the velocity is less. The blood have a more of a density compared to the organs, right? And along with the density, the characteristic of the one molecule to transfer the sound energy to the another is more in a blood. So the blood has the highest velocity and the air is the lowest one. Now, the sound is keeping a transmit with the constant velocity in the throughout the same medium, but they lose the energy when it's passed through. But the one medium and second medium are come together, that is a boundary of that. That time, the reflection of the sound will occur. So, next question, which frequency of the sound wave is used in the ultrasonographic machine? 2 to 20 hertz, 2 to 20 kilohertz, 2 to 20 megahertz, all of the above. The 2 to 20 is infrasonic, 2 to 20 kilohertz is a sonic, that means we can hear that voice, and 2 to 20 is ultrasonic. Got the answer? Good. Okay. Only 5 people participate. Okay. So when one sound wave transmit to the another, right, and the both the medium have a different of the density, so what happen is transmit back. So when you know the you go for the auditorium or somewhere, you have a most of the panel which is absorb the echo, otherwise it reflects back. Okay. So when the air it's touching to the another medium, it is going to most of reflex, and they have the same density, the most of the wave pass through, and lesser is the reflection one. So what happened? The air is the enemy of the sound wave. So in that case, EBUS we are using the NS, right, normal saline, or the water or distilled water to overcome that effect of the air. Some people are used to without balloon, they are doing very well the EBUS, and sometimes we use a normal saline about the 1 cc or 2 cc when you lose the contact with the wall. So during that time, endobronchial secretion work as a transmit medium. So in a radial EBUS, there's a movable transmitter providing a 2D image and it's continuous rotating. I come on the detail after that. And this is image produced is a B mode. On B mode, further we go for a color Doppler. That is the two things. It's a single color Doppler which provides the velocity and direction of the blood flow. That can demonstration based on the blue color and the red color, and the power power mode of the Doppler scan, which show the extension of the blood flow, which is help you to see the smaller vessel which is passing through the targeting site. Okay, and to avoid the bloody sample, you can avoid that part, and that the power color mode will help you. So now coming to the depth of the penetration, you have a higher the frequency, you have a good resolution, but the higher frequency cannot travel the beyond. So you can compromise the depth, while the lower frequency which travel most of the depth, but they loosen their detailing of that. So when you do the radial EBUS, you have a higher frequency about 20 hertz, because the penetration is about 2 to 5 centimeter, and you can see the very well architecture of the bronchial wall and all the layer of epithelium lining and the wall. While in a linear EBUS, we use about 2 to 5 the megahertz, can increase up to the 10 megahertz, and that frequency you require the more of penetration. So up to the 5 centimeter of the depth, you can have a good clearance of the idea. So you can see here the 12 megawatts, the resolution is lesser, the penetration is good. While the high megawatts, the 13 megawatts, you can see the resolution very good, but the penetration is lesser. As in mechanical scanning, that in a radial EBUS, the rotating motor produces the transducer, while in a linear, the electropiezo is lying over the surface of the linear EBUS. So that will see the screening difference, the 360 degree, and you have about the 60 degree. The electric transducer is produced here, the sound wave travel through the bronchial wall to the tissue and reflect back, and the picture is produced over your the screen. Now the most of the people are using EUME2. This port is for the real EBUS. This port is for a linear. Now coming to the main topic is the knobology. Right? The knobology is whatever the knobs button which is available on a keyboard of the ultrasound, how to use it. First is on and off. So the 0 is given for the off and the 1 is given for the on universally. So the first is you have to switch on the power. Before that you have to attach your radial probe or a linear probe, ultrasound cable with it. Then you have a preset setting, but sometimes it's not in R. Now next is after starting your EBUS screening of a mediastinal lymph node, go for the depth. Usually we set the depth is a 4, but the whatever the targeted tissue, the depth from a bronchial wall, the distance from a bronchial wall to the tissue, you have to manage the depth according to that. But most of us, we are habitual to use the depth of 3 to 4. We are not going for maybe a 2 or the 1 because it's a very larger image which create on your screen. So in your keyboard, you have adjustment button of a depth and a range. Now the gain. The how dark or the bright you want to see your image which is appear on the screen. It's a very subjective. My eyes want to see the gain about the 50 and 5. Sometimes some people want a 16 and 4. Sometimes a 19 and 7. So it's totally a different. But it's a range. Okay? And you have to adjust the gain plus or minus on base of your on keyboard. You can see here the gain, according to gain, the images get the darker. Are you reducing the gain? Now it's a 1, 0. It's almost darker, but you can see the lymph node and demarcation of the part is very brighter. Now increase the gain. You can see the lymph node is get enhanced. The boundary is the very well, which is echogenic right now. So according to the gain adjustment, you can visualize a lymph node, that target tissue. Here you see how the contrast is going to change the echogenicity of the lymph node. So needle inside the node, the contrast is 2, the gain is 13. You can see the more of the brighter spots are coming here. It's the gain contrast increase, and this is very much of brighter. But the detailing which we lost, so between the two necrotic area and the semi-solid area, you have a very much of differential, and because of that, the brightness, you may lose sometime the nearby, the structure or characteristic of the node. This is also the near and far field adjustment and time gain compensation. Because of that gaining adjustment and the difference between the two tissues, that can be adjusted with the time gain compensation. The focus is adjusted by the green dot here, is a triangular shape, right? So mostly we use the focus where the demarcation of the lymph node to the blood vessels or the other structures. So we can see the very well the boundary of the lymph node. Okay, we should not penetrate beyond it. The focus, when we have to adjust.
Dr. Varun, you have 2 more minutes.
Yeah. Okay, I'm going to complete it. The focal zone will identify the lateral resolution between structure to structure and the axial resolution by the above and below structures. The freeze button, you can, for a more detailing, you can freeze the button and you can see what are the characteristic of the node. Now coming to the latest one is a ME3. So I think the previous lecture is very well covered on ME3. I'm not going to detail on that. The processor look like outside is the same, but the feature is good in that. The tissue harmonic imaging is the more. That improves the image quality by eliminating the weak echoes that could the image when the fundamentally frequency and the transmitter is used in that. So in that one we have improved the resolution with the THE, fewer the artifact, and improve the signal and the noise ratio. So you can see here the penetration mode and the resolution mode. the demarcation of the lymph node is improved by the penetration and the resolution mode. You can see the difference between ME2 and ME3. The more of the sharp boundaries, more of the clear-cut differentiation between the two structure compared to the ME2. There is a low echo resolution. You can see here, I'm just skipping a slide. So you have a better with the gain, the contrast, structure enhancement, low echo reduction, and a tissue harmony echo resolution mode. The flow, they have another one is power flow and then edge flow. So that is a just new advantage of ME3 over ME2. Thank you so much for hearing. Any questions?